we continue with our discussion with the consideration of forces that are acting when we are considering the Newton's laws of motion. So we have to consider all the forces, the net forces F equal to ma, and on the right hand side all the forces are to be considered, the pressure forces, the surface forces, and so on. Now, in just our previous discussions, we showed you some gadgets, some utilities in which the entrance point and the exit point of the flow, of the fluid flow, is sometimes equal, sometimes smoothly done, but in many cases they are not the same. The situation can be different, and therefore the fluid flow flux cannot be calculated as easily as we can do in a smooth geometrical condition. And in that kind of situation, we need a correction factor, and the researcher found out that if we use a small factor called as beta, normally this is what they write, then if we substitute that into the equation, then it gives the right result, and that they are verified experimentally. So velocity across most inlets and outlets is not uniform many times. The controlled surface integral equation 6.17 that was shown to you earlier, and that is all it contains is the surface forces or surface integral, and it is converted into algebraic form using a dimensionless correction factor. These numbers, the factor or the Reynolds number or Mach number or this kind of numbers that we use to treat mathematical equation, to smooth out the equation balance and simplify the physics of, let us say, the fluid flow, because this is a very subject which is engineering, physical, and also mathematical. It's a combination of several things, and everything has to be taken into account. So to balance the equation, we use a dimensionless correction factor beta. So it's a small constant. We call it as, it is named at momentum flux correction factor. So small factor that results in the correction of the equation, and so this equation 617 that is referred above is adjusted as this. So you can see that in this term, in the controlled system term, we have inserted beta at the outlet as well as at the inlet, and the velocity is taken to be the average velocity that flows, that is found in the flow field conditions. So momentum flux across an inlet or outlet is represented by this integral, and beta, the correction factor, can be calculated from this ratio, and this ratio, as we commented, is dimensionless. If we write down the dimension of everything that is there, the density, velocity, etc., area, and similarly, then each dimension will neutralize itself and it will result as a dimensionless number. So momentum flux correction factor, if we have to write it, what is it? Then this is equal to this integral. And beta is always greater than or equal to 1. It has been found experimentally and mathematically also. It's close to 1 for turbulent flow. So if the flow is turbulent, normally it's close to 1, but it's not very close to 1 if the flow is developed in a laminar format. Now, laminar format, I have shown you in many times the picture in which the flow is very smooth. Sometimes it takes a parabolic shape, another times it's something like this, but it's a smooth flow field situation. So that is the status, and obviously to treat turbulent flow situation is very difficult, but in real conditions one has to deal with that also. So these are the momentum flux factor, and we have defined it as this.